Hi all, I am Dr. D. Senthil Kumar, working as Assistant Professor in the Department of Mechanical Engineering. In this lecture, we are going to deal with the theory of metal cutting in the course machining process. Actually, what is theory of metal cutting? Metal cutting is the process of producing workpiece by removing unwanted material from a block of metal in the form of chips. The major drawback of the process is the loss of material in the form of chips. The process is basically adopted because of the following reason: to get higher surface finish, to achieve close tolerance, and to get complex geometrical shapes. The process of metal cutting in which the chip is formed by is affected by a relative motion between the workpiece and the hard edge of a cutting tool held against the workpiece. Such relative motion is produced by a combination of rotary and translating movements either of the workpiece or of the cutting tool or of both. Depending on the relative motion, the processes are called either turning or planing or boring or other operations. Material removal process. These processes are adapted to get higher surface finish, close tolerance, and complex geometric shapes which are otherwise difficult to obtain. This is most expensive because a substantial amount of material is removed from the raw material in the form of chips to achieve the required shape. Invariably, all components undergo a material removal operation at some points. A machine tool is the one which is holding the cutting tool, is able to remove the metal from a workpiece to generate the required part of the given size, configuration, and finish. Then we are now dealing with metal cutting. It's a process where a stronger metal is used to cut a softer metal. Parts after heat treatment are usually distorted and hence need machining. This material removal can produce சார் சொல்லுங்க சார்.
ஹலோ
சார் சொல்லுங்க.
நீங்க நாளை வந்து தேர்தல கொடுத்துட்டு போறீங்களா இல்ல உள்ள மட்டும் கொஞ்சம் இன்ஃபார்ம் பண்ணுறீங்க சார். ஏன்னா நாளைக்கு லீவு
சார் கேட்ல தான் கொடுப்பேன். கேட்ல தான் கொடுப்பேன் சார். கேட்ல தான் கொடுப்பேன். ஓகே சார். ஓகே. Metal cutting will produce accurate dimension and sharp corners. It will also produce desired structure such as shiny finish, mirror surface, etc. With modern machine, metal cutting can be done in an economical manner. But metal cutting has some disadvantages also: higher cost of labor and tools, scrap metal results, and long cycle time. Then we will see about the types of cutting tools. There are two types of cutting tools generally: single point cutting tool and multi-point cutting tool. Single point cutting tool has a wedge-like action and finds wide application on lathe, shaping, and slotting machines. It is the simplest form of tool. In multi-point cutting tool, we will have two or more single points arranged together as a unit. Example, milling cutter and broaching tool. Now we are entering into the theory of metal cutting. Actually, in metal cutting, there are two basic methods using a single point cutting tool. One is orthogonal or two-dimensional cutting. Next one is oblique or three-dimensional cutting. Orthogonal or two-dimensional cutting takes place when the cutting face of the tool is 90 degrees to the line of action of or path of the tool. The cutting edge is straight and it is set in a position that is perpendicular to the direction of the primary motion. This allows us to deal with the stresses and strains that act in a plane. In oblique cutting, the cutting edge is set at an angle to the direction of the tool. This is the case of three-dimensional stresses and strain conditions. Here, in this figure, we can see that the cutting face of the tool is perpendicular to the direction of motion of the tool. And here, in oblique cutting, we can see that the cutting face of the tool is inclined to the direction of motion of the tool. Here also we can see it clearly. This is perpendicular to the direction of motion and this is inclined to the direction of motion. So when orthogonal cutting takes place, the chip flow will be in this direction, and in oblique cutting, the flow of chips will be in this direction. Orthogonal cutting is mainly confined to knife turning, broaching, and slotting. Bulk of machining is done by oblique cutting. Force which cuts or shears the metal acts on larger area. So oblique to have a longer life as the heat developed per unit area due to friction along the tool workpiece is considerably small. Also, it will remove more metal in the same life as an orthogonal tool. Then we will deal with mechanics of chip formation. Look at this figure. Here, the tool is considered stationary and the workpiece is considered to be moving towards the right. Due to the cutting action of the tool, the metal is severely compressed near the front of the tool. It causes high temperature, shear, and plastic flow if the metal is ductile. When the stress in the workpiece just ahead of the cutting tool reaches a value exceeding the ultimate tensile strength of the metal, the particles will shear to form a chip element which moves up along the face of the tool. The outward or shearing moment of each successive element is arrested by work hardening and the movement is transferred to the next element. The process repeats itself and a continuous chips is formed having burnished underside and serrated topside by shearing action. The plane along which the element shears is called shear plane. So the chip is formed by plastic deformation of the grain structure of the metal along the shear plane. Look at this figure. Actually, the deformation does not occur sharply along the shear plane. Rather, it occurs along a narrow band. The elongation begins at the region AB and the deformation gets completed at the region CD. The region between AB and CD is known as shear zone or primary deformation zone. But the two lines AB and CD may not be parallel, but produce a wedge-shaped zone which is thicker near the tool face at the right than at the left. It is one of the reasons for curling. Another reason for curling of the chip is the non-uniform distribution of forces at the chip tool interface and on the shear plane. The shear plane must be curved concave downwards. In this figure, we can see the curling of chips when the tool is in cutting action. We have to consider some important factors in all machining processes. Some of the important factors include geometry of the cutting tool, machining conditions, including tool speed, work hardness, and tool hardness. Some other factors include work holding devices, fixtures, the coolant which we use, the process which we adopt, some accuracy issues, and some machining conditions such as stiffness. These are all the important factors which we have to consider during the machining process. Next, we are going to see is types of chips. There are three types of chips: discontinuous or segmental form chips, continuous or ribbon type chips, continuous chips with built-up edges. A discontinuous chips comes off the cutting tool as small chunks or particles. This type of chips is obtained in machining most brittle materials such as cast iron and bronze. These materials rupture during the plastic deformation and form chips as separate small pieces. Tool life is also reasonably good and the power consumption is low. Discontinuous chips can also be formed on some ductile materials if coefficient of friction is low but poor surface finish and short tool life will be produced. A continuous chip consists of elements bonded firmly together without being fractured. It looks like a long ribbon with smooth shining surface. This clip may be indicating ductile work materials and fine fits and high speeds. Chip under the microscope shows no signs of tears or discontinuities. The upper side has small notches while the lower side is smooth and shiny. The continuous form is considered most desirable for low friction at the tool chip interface, low power consumption, long tool life, and good surface finish. The term built up. It appears that when the cut is started in ductile materials, a pile of compressed and highly stressed metal forms at the extreme edge of the tool. Owing to the high heat and pressure generated there, this piled up metal is welded to the cutting tip and forms a false cutting edge to the tool. This is usually referred to as the build-up edge. Okay, these are the three types of chips we have seen. Now, what is the use of a chip breaker? A continuous type chip forms a long cut, fouls the tools. Clutter will fill up the machine and the workpiece. They should be broken into small pieces for the ease of handling. Hence, chip breakers are used to reduce the swap, that is, waste chips into small pieces as they are formed. Chip break and chip curl may be promoted by the chip breaker. There are some types of chip breakers available. One is by clamping sheet metal in the path of the coil. Next one is a stepped type breaker in which a step is ground on the face of the tool. The next is an integral type chip breaker, where a groove is ground behind the cutting edge of the tool. And finally, a clamp type breaker, in which a carbide faced plate or clamp is braced on the face of the tool. So in this lecture, we have seen what is metal cutting, what is orthogonal cutting, what is oblique cutting, what are the what is the mechanics of chip formation, what are the types of chips, and what is the use of chip breaker. Thank you.